Welcome to AI Frontiers, where cutting-edge machine learning research takes center stage. Today's presentation explores recent advances in machine learning, highlighting innovative approaches and breakthrough findings that are shaping this rapidly evolving field. Machine learning continues to develop at a remarkable pace, transforming how complex problems are approached across numerous domains. The papers discussed today represent significant contributions to this dynamic field, offering valuable insights into current research priorities, methodological innovations, and potential future directions for machine learning technology. Machine learning occupies the intersection of computer science, statistics, and mathematics, forming both the theoretical and practical foundation for numerous artificial intelligence applications. Over the past decade, machine learning has transformed from a specialized academic pursuit into a mainstream technology driving innovation across industries. From healthcare diagnostics to financial forecasting, autonomous vehicles to content recommendation systems, machine learning technologies have become increasingly integrated into daily life. The significance of machine learning research extends beyond technical achievements. As these technologies become more powerful and widespread, they raise important questions about reliability, safety, interpretability, and ethical implementation. Many current research papers address these challenges directly, proposing novel approaches to make machine learning systems more robust, transparent, and aligned with human values. The field encompasses several fundamental approaches including supervised learning, where models train on labeled data to make predictions, unsupervised learning, where models identify patterns in labeled data, and reinforcement learning, where agents learn optimal behaviors through environmental interaction. The first major research theme emerging from recent publications involves state-space models as alternatives to attention-based architectures. These models offer significant advantages through linear scaling with sequence length, compared to the quadratic scaling typically observed in attention mechanisms. This characteristic becomes particularly valuable when researchers tackle increasingly complex tasks involving very long sequences. Boyer and colleagues made notable contributions in this area with their introduction of damped linear oscillatory state-space models. These models improve upon previous oscillatory state-space approaches by learning to dissipate latent state energy across multiple timescales. This advancement enables better long-range reasoning capabilities while simultaneously reducing the hyperparameter search space by 50%. The efficiency gains and improved performance make state-space models increasingly attractive for sequence modeling tasks that would otherwise be computationally prohibitive with traditional attention-based approaches. Continuing with the first research theme, recent work has significantly advanced understanding of transformer capabilities for in-context learning. Liu and colleagues conducted extensive examination of how transformers function during in-context learning tasks. Their research revealed that these models implicitly learn both prior distributions and effective regularization strategies autonomously. This capability represents a fascinating bridge between traditional machine learning approaches and emerging neural methodologies. The ability to develop internal regularization mechanisms without explicit programming highlights the sophisticated learning capabilities of transformer architectures. Additionally, these findings demonstrate how transformers enhance adaptability to new tasks with minimal examples, effectively performing few-shot learning through their attention mechanisms. This research provides valuable insights for designing more efficient and adaptable neural network systems that can quickly generalize from limited training examples. The second major research theme focuses on robustness and reliability, addressing key challenges in deploying machine learning systems in real-world environments. Recent publications emphasize techniques for making machine learning systems more dependable in unpredictable settings. This includes developing methods for handling distribution shifts, where test data differs significantly from training data, and defending against adversarial examples designed to fool models. Researchers are also advancing techniques to quantify uncertainty in model predictions, allowing systems to express appropriate confidence levels or abstain from decisions when necessary. Additionally, significant work addresses approaches to ensure consistent performance across diverse datasets, preventing models from exhibiting disparate accuracy across different demographic groups or data sources. These efforts collectively aim to bridge the critical gap between laboratory performance metrics and production reliability requirements, ensuring machine learning systems function consistently and safely when deployed in real-world applications. The third prominent research theme centers on interpretability, efforts to open the black box of complex machine learning models. Researchers are developing sophisticated methods to understand model decision processes, making previously opaque systems more transparent to both developers and end users. This work navigates the essential balance between performance optimization and explainability, recognizing that the most accurate models are often the least interpretable. The field distinguishes between post-hoc explanation techniques, which analyze already trained models, and inherently interpretable models designed with transparency as a core feature. Visual analytics for neural network interpretation have advanced significantly, allowing researchers to visualize activations, attention patterns, and feature importance. These interpretability efforts address not only technical needs but also respond to increasing regulatory and ethical requirements for transparency in automated decision systems, particularly in high-stakes domains like healthcare, finance, and criminal justice. Synthesizing findings across the research landscape reveals several critical insights about the current state of machine learning. State-space models have emerged as a competitive alternative to attention mechanisms, offering comparable performance with better computational scaling properties for long sequences. In-context learning capabilities demonstrated by transformer models have surprised researchers with their effectiveness, suggesting these architectures implicitly learn meta-learning strategies. Despite advances in model efficiency, fundamental trade-offs between model size, training data requirements, and performance continue to present challenges. While interpretability techniques have become increasingly sophisticated, they remain limited when applied to the most complex models, creating ongoing tension between performance and explainability. Finally, research consistently shows that domain-specific adaptation remains crucial for real-world applications, with general-purpose models requiring significant customization to achieve optimal performance in specialized contexts. Researchers are employing diverse methodological approaches to tackle machine learning challenges. Empirical studies featuring large-scale experiments and ablation studies provide practical insights into model behaviors under various conditions. These are complemented by theoretical analyses examining model properties and establishing mathematical convergence guarantees. Hybrid approaches that combine neural networks with symbolic reasoning show promise for improving both performance and interpretability. The development of standardized benchmarks has become increasingly important for enabling fair comparisons across different research efforts. Case studies demonstrating real-world applications and their limitations provide valuable context for understanding how theoretical advances translate to practical implementations. This methodological diversity reflects the multifaceted nature of machine learning research, which requires both theoretical rigor and practical validation to advance the field effectively. Taking a closer look at selected research, Boyer and colleagues addressed fundamental limitations in state-space sequence modeling with their paper on damped linear oscillatory state-space models. This work introduces an innovative damping mechanism designed to dissipate latent state energy, a critical advancement for maintaining stable representations over long sequences. The model operates across multiple timescales, enabling improved reasoning capabilities for both short-term and long-term dependencies in sequence data. A particularly notable achievement is the reduction of the hyperparameter search space by 50%, significantly decreasing the computational resources required for model optimization. This research represents a significant advancement in efficient sequence modeling, offering an approach that maintains high performance while addressing the computational scaling challenges that have limited previous state-space models. The damping mechanism provides a theoretically sound solution to the stability-expressivity trade-off that has challenged sequence modeling approaches. Liu and colleagues made substantial contributions to understanding transformer capabilities in context learning. Their research provides a comprehensive theoretical framework for understanding how transformers perform in context learning tasks, connecting neural network behavior to principles from statistical learning theory. The work demonstrates that transformers effectively learn implicit prior distributions over task spaces during pre-training, allowing them to rapidly adapt to new tasks that share statistical properties with previously encountered data. Perhaps most intriguingly, The research reveals how these models autonomously develop regularization strategies without explicit programming. This capability bridges an important gap between traditional statistical learning theory and modern neural network approaches. The insights from this research offer valuable guidance for designing more efficient few-shot learning systems, suggesting specific architectural modifications and pre-training strategies that can enhance in-context learning performance across diverse task domains. Recent advances in machine learning interpretability have produced novel frameworks for explaining complex model decisions. These approaches combine local and global explanation techniques to provide comprehensive understanding at both the individual prediction level and the overall model behavior level. Researchers have validated these interpretability methods across multiple domains including healthcare and finance, demonstrating their effectiveness in high-stakes decision contexts. The research illustrates how interpretability can enhance model development itself, with explanation techniques revealing biases and failure modes that might otherwise remain hidden. Additionally, these advances provide practical tools for stakeholder communication, helping bridge the gap between technical experts and domain specialists or end users. By making model reasoning more transparent, these interpretability frameworks address a critical need for accountability and trust in machine learning systems, particularly as they become more deeply integrated into consequential decision processes across society. Looking toward the future, several clear research directions are emerging in the machine learning field. Further development of efficient alternatives to attention mechanisms continues to be a priority, with researchers seeking architectures that maintain performance while improving computational efficiency. The integration of causal reasoning with deep learning approaches represents another frontier, potentially addressing limitations in current models' ability to generalize beyond correlational patterns. Advances in few-shot and zero-shot learning capabilities remain highly sought after, particularly as researchers aim to reduce the massive data requirements of current systems. Addressing data efficiency and computational resource constraints has become increasingly urgent as environmental and economic concerns about large-scale model training grow. Finally, developing standardized benchmarks for robustness and interpretability will be essential for measuring progress on these critical dimensions that extend beyond simple accuracy metrics. This presentation was created through a synthesis of artificial intelligence technologies working in concert with human expertise. The content was synthesized using Anthropic's Claude 3-7 Sonnet 20,250,219. Drawing from a comprehensive analysis of recent machine learning literature. Text-to-speech synthesis was performed using OpenAI technologies to create the audio narration. Visual elements throughout the presentation were generated with Google's image generation tools, designed to complement the technical content. Human expert review was conducted at multiple stages to ensure accuracy, coherence, and appropriate technical depth. While this presentation has been thoroughly reviewed, some oversights may exist in the synthesis process. All references to original research papers have been provided to enable further exploration of the primary sources discussed throughout this presentation. To stay updated on cutting-edge machine learning research, subscribe to the AI Frontiers channel. New presentations synthesizing the latest machine learning papers are released every week, providing accessible overviews of important developments across the field. Join a growing community of researchers and machine learning enthusiasts who engage with these topics through comments and discussions. Share thoughts and questions in the comment section below each video to participate in the ongoing conversation about machine learning advances. Feedback from viewers helps improve content quality and topic selection for future presentations, ensuring the channel remains valuable and relevant to the community's interests. Thank you for watching this exploration of recent advances in machine learning research.